Hey everyone, welcome to this explainer. I am absolutely thrilled to be guiding you through today's topic. We're looking at a truly fascinating evolution in engineering, the closed-loop control of electric drive systems. If you've ever looked at complex machinery and wondered how on earth it moves with such perfect grace, well, you are exactly in the right place. Today, we're setting the stage to demystify the complex math and physics that make modern electric drive control possible. Okay, let's dive into this. Here is a quick look at our roadmap. First, we'll establish the baseline with DC motor modeling. Second, we'll look at the brain of the system, the PID controller. Third, we'll tackle the AC challenge of scalar control. Fourth, we'll reveal the ultimate solution, field-oriented control, or FOC. And finally, we'll unpack the magic math of the Park transform. Let's get right to it. But before we get to the formulas, I want you to think about this for a second. How exactly does a massive, heavy industrial robot arm swing around at blazing speeds, carrying heavy loads, and yet stop with literal sub-millimeter precision, right? There's no magic here. It's high-stakes, real-world applied mathematics. And the secret behind all this incredibly precise movement is what we call a closed-loop system. So what actually is a closed-loop system? Essentially, it's a continuous feedback cycle. The system is constantly monitoring variables, like the actual speed or position, comparing them against what we want the system to do, and then instantly readjusting the power converter's output to fix any difference. It's this relentless cycle of checking and adjusting that serves as the beating heart of all precise motor control. All right, to really grasp how this feedback loop works in complex systems, we first need to lay down the foundational physics. So, Section 1, the baseline of DC motor modeling. Now, what's really interesting here is how we translate the physical realities of a separately excited or permanent magnet DC motor into a pure mathematical model. We look at differential equations representing electrical and mechanical dynamics, and by introducing small perturbations, we can extract the DC and AC components. This lets us model exactly how DC drives interact with switch-mode power converters. And by using Laplace transformations, those S variables, we basically turn complex time-based calculus into much more manageable algebraic equations. This tells us exactly how the converter voltage impacts the physical output of the motor. Let's break down how this builds a complete picture in 4 clear steps. First, we've got the voltage equation, or VA. This is the electrical power being fed into the motor. Second, that power generates electromagnetic torque, TE, literally our spinning force. Third, as that motor spins, it acts just like a generator, creating a reverse voltage called back EMF, EA, which pushes back against our input. And finally, all of this interacts with the load torque and inertia, which is just the physical resistance of whatever we're trying to move. It's absolutely a perfect mathematical balancing act. But, just having a mathematical model of a motor isn't enough on its own. We need something to drive it intelligently based on that feedback loop we talked about earlier. So let's move to Section 2 and introduce the absolute brain of the operation, the PID controller. To actually control this system, we incorporate a PID compensator right in the Laplace domain. It starts with the input error variable, designated as E of t, which is literally just the difference between our desired speed and our actual speed. The transfer function then calculates the command voltage, VDC. In the Laplace domain, this is represented as VDCS equals the error multiplied by the sum of our proportional constant, Kp, the integral term, which is 1 over s times Ki, and the derivative term, s times Kd. Let's completely demystify this PID acronym, because once you get this, all that Laplace math feels entirely intuitive. Just think of it as present, past, and future error correction. The proportional part looks at the present, basically how big is the error right now. The integral part looks at the past. It accumulates past errors over time, calculating the area under the curve to make sure we don't have some lingering offset. And the derivative looks into the future. It checks the slope or rate of change to predict where the error is heading so it can softly apply the brakes. Put them all together, and PID gives us incredibly smooth, precise control. Now, DC motors are relatively straightforward to model and control, right? But the industry relies heavily on induction motors, which use alternating current, or AC. This brings us to Section 3, the AC challenge, and our first attempt at solving it, scalar control. Induction motors are a bit tricky because their speed depends on the AC supply frequency. With closed-loop scalar control, we take the reference speed and compare it to the actual speed to find our error. Simple enough. Then a PI controller takes that error and generates a slip command. A limiter steps in to ensure this slip doesn't exceed the motor's maximum torque range, which is absolutely crucial because if the slip gets too high, the motor enters an unstable region and just stalls out. Finally, by keeping the voltage and frequency strictly proportional, we generate the final command of the inverter. It definitely works, but as we'll see, it has its limits. And that brings us to the climax of this explanation. When scalar control just isn't cutting it for highly demanding applications, we turn to the gold standard for high-performance electric drives. Section 4, the ultimate solution, field-oriented control, or FOC. Let's quickly contrast these two methods so you can see exactly why FOC is such a game changer. With scalar control, it's super simple to implement because it just keeps voltage and frequency proportional, but the trade-off? A pretty sluggish dynamic response. You definitely can't use it for that high-speed robot arm we talked about earlier. On the other hand, vector control, or FOC, requires a highly complex mathematical implementation. However, by decoupling the magnetic flex and the torque, it delivers extremely precise, high-end dynamic performance. The system-level block diagram for field-oriented control brilliantly illustrates what that complexity actually looks like in practice. I know, at first glance, it looks like an intimidating bowl of alphabet soup. We've got the Clark transform converting three-phase currents into two stationary axes, the Park transform rotating them, and multiple PID controllers managing the whole flow. But don't worry, we're going to break down exactly how this works. Before we start tracing lines on that complex logic, we need to understand the core philosophy at play here. The entire reason FOC works is a literal magic trick called decoupling. Decoupling torque and flux is a mathematical process that takes the highly complex, nonlinear, tangled mess of a three-phase AC motor and allows our software to treat it exactly like the simple, highly controllable DC motor we were modeling back in Section 1. So, tracking back through that logic, here's how the theoretical math becomes real physical movement. First, a speed calculator feeds the actual speed back into the loop to find our error. Then, dedicated PID controllers manage the now isolated currents, one for the direct current, which controls the magnetic field, and one for the quadrature current, which controls the torque. Next, an inverse Park transform takes these simple DC-like commands and converts them right back into complex AC waveforms. And finally, the space vector PWM, or pulse width modulation, translates those waveforms into rapid electrical pulses, physically firing the switches in the three-phase inverter to drive the motor. It is honestly a stunning piece of engineering. But you might have caught a specific term I just used there, the Park transform. How exactly are we isolating those currents in the first place? Let's lead right into our final technical section to look at the specific mathematical mechanism making all of FOC possible. The Park transform is quite literally a mathematical time machine. It was invented all the way back in 1929 by Robert H. Park. And what it does is take a rapidly alternating three-phase AC system and transforms it into a stationary two-quadrant DC system. Think of it like this. If you're standing next to a spinning merry-go-round, the horses are constantly zooming past you in this chaotic wave. But if you step onto the merry-go-round and spin with it, the horses suddenly appear totally stationary relative to you. The Park transform steps onto the rotating magnetic field of the motor, and suddenly those chaotic AC waves become steady, easy-to-control DC values, the direct component for flux and the quadrature component for torque. Mind-blowing, right? It is truly amazing to think about. An equation sketched out on paper nearly a century ago is the exact mathematical key that allows our most advanced modern robotics and electric vehicles to move with absolute perfect grace today. Which leaves us with this final thought. If pure mathematics from 1929 can entirely transform the physical limits of modern hardware, what invisible software algorithms being written right now will dictate the physical world of tomorrow? Keep learning, keep questioning, and I'll see you in the next explainer.